Thank you for this nice invitation. I'm very happy to be here, and I thank the organizers, and I'm particularly happy to see Fernando. Usually we meet in Brazil or in summer, which is the same. And okay, I'm sorry, I already lost the stuff. Okay, so I didn't change the title. It turns out that I sent the title last December, and then when I arrived here, I prepared a lecture, and I realized two days ago that it was different from the previous title. But well, it's not that different. The core of the subject is the same, and the techniques are the same also. But this is what happens when you invite old people. They have a tendency to forget everything. So, okay. So the second point is that I will not talk about a subject which is in the core of this workshop. It's not geometric analysis. It's rather close to geometric group theory. So rather than going quickly to the theorem, I will take my time and explain examples and why we are interested with this. Okay. Okay, so the story is, starts with a metric space. So the goal is to do, the ultimate goal is to do geometry of metric spaces. So let's call it X, D. So I will usually consider locally compact metric space. Later on, I will add some other properties, but for the moment, for the time being, it's okay with this. And I assume, so it's a geometric group theory, so I will assume that there is a discrete subgroup of the isometric group of X, of this metric space, which acts, as usual, properly discontinuously on the space X, and in such a way that the quotient is compact. And when I come to manifold, I will ask the manifold to be not only compact, but closed, that is without boundary. And we'll add another data. I assume that there is a Borel measure nu invariant by the group. And well, with this, can define the first word in this new title, which is the entropy, quite different from the entropy introduced by Jacob in his talk. And this is a classical invariant. I take the volume of balls of radius r. X is a point in the metric space. And I'm interested in the exponential rate of growth of this volume. So I take a logarithm, 1 over r, and the limit. So in this situation, the limit exists, and call it the entropy of x d. Okay, so this is the main character of this lecture. It's called entropy because in some instances it's related to the entropy of the geodesic flow for manifold, for example. Really the entropy that one defines in information theory. I'll come back to this a little bit later. So there are two examples which I want to discuss today. So I'll put the first one here, the second one on the other side. It will forces me to walk from one side to the other. So the first example is about groups. So let's take gamma to be a finitely generated group. And this discrete group. And S, a finite generating set. So there is a classical construction, which I recall now, which is the construction of the so-called Cayley graph of gamma using S. And so it starts like this. So S is a list of generators, for example, J1, Jk. And start by putting a point at the identity and an edge of length 1 for each generators, G1, G2. And I ask another hypothesis for the sake of simplicity, that the generating set is symmetric in the sense that if J is inside, G minus 1 is inside. So let me do the picture with two generators. And you keep going, adding generators. Eventually, you reach a point where there is a relation. It gives a cycle, and keep going up to infinity, if any. Okay. So this graph here has the property that so we endow this graph with a distance, which is considering the edges as being isometric to the interval 0, 1. And so we get a graph called the Cayley graph associated to the group and the generating set with a distance which I call d sub s. Now if we take for nu the counting measure, that is the sum of, maybe I will call these elements gamma later. So not only I change the title, but I'm changing notation during the lecture, so it's even worse. The counting measure, which satisfy the properties. And this allows us to define so-called entropy with this formula of gamma with respect to S. Okay, so this is one particular case of this situation. And that will play a big role in the sequel. So the second example is more classical, although this one is classical too. It's for manifolds. So let's think of X. Sorry, X will be the universal cover. Here it's a manifold, so closed manifold. And we assume that it is a Riemannian manifold, so there is Riemannian metric. So we look at the universal cover, X twiddle. So this X twiddle would be this X over there. And it is endowed with the distance, of course, the G twiddle, like this. And there is a natural measure, which is the volume element associated to the metric. And this defines something that we call the entropy of X tilde d J tilde, but for sake of simplicity, I will call entropy of X G. Okay. So this is quite simple. Okay, so here, this number, which is an asymptotic invariant, depends on the generating set. And on the other side, the asymptotic invariant depends on the Riemannian metric or its leaf, which is more or less the same. All right. And so the question I want to discuss is what relations between them? Well, what relations between the entropy of a manifold with respect to some metric and the entropy of its fundamental group with respect to, well, I'm sorry, entropy of the Cayley graph of its fundamental group with respect to any finite generating set. So this is a very old question. In fact, the question of the growth of the universal cover of a manifold compared to the growth of the fundamental group. And it goes back to the 50s. I'll be more precise later. All right, so question is clear. Let me give some, so this was an introduction. Let me give some examples and some results, standard results, which I will give in these two different situations. So let's talk about case 2. This is this case. The thing I want really to explain is not only the words in this title, but the words in the previous title. And so the first trivial remark is that if the Ricci curvature of the metric is bounded below, so let me write it this way, as we usually do. So the eigenvalues are bounded by minus n minus 1. Then we can compare the entropy to the entropy of the case when there is equality, in particular case, which is the real hyperbolic space. Then is less than n minus 1. And her whole story starts here, actually. This invariant here is weaker than a lower bound on the curvature. So the goal is to replace any lower bound of the Ricci curvature by an upper bound on this. So this explained in the other title there was almost without curvature. So that we hope to replace lower bound on the Ricci curvature by an upper bound on the entropy, which is much weaker because it's an asymptotic invariant. And why do we want to do that? Well, the ultimate goal is to work with metric spaces where you can not always do differential geometry and compute tensors and these kind of things. And also it's a revenge. I mean, when I was starting, tensors were a nightmare, so I decided to take a revenge. Okay, so as I said, the entropy depends on the metric, but not, so let me say it again. This depends on G, but not the fact that it is positive. If it is. So in other words, if it's positive for one Riemannian metric, it's positive for any other, and it's a trivial thing. The metric space that you obtain are quasi-isometric, and it's easy to check. So the story started long time ago, and there is a theorem, so comparison between the two, which is usually called Milnor-Schwarz theorem, which says that the growth on the universal cover of a manifold is exponential, meaning that this is positive, if and only if the growth of the group, so I call it for any of the fundamental group for any generating set is also positive. Okay, so the story is that this idea of comparing the growth of the fundamental group with the growth of the universal cover of a manifold goes back to Efremovich. I think it's 1953. But the seminal paper is a paper by Schwarz. 1958, which contains a lot of information. No, sorry, 55. And Milnor wrote another paper, 1968. So obviously he didn't know Schwarz paper. If you remember, you are maybe too young. But at the time, the communication between the two countries was not completely fluid. Anyway, this is a very first result in this spirit. Okay. So let me come to the other case. So the case one, there is more to say in that case. So the erasing is not what I do best. There is more to say. The first remark is that as before, for a finitely generated group, entropy of gamma S depends on S. but not the positivity. Again, for the same reason, to change the generating set into another finite generating set, then the two graphs are quasi-isometric, right? And well, the first test is to compute. So this is the entropy of the free group in R generators with respect to the standard generating set, taking the generators which makes the group free. And one gets something like log 2R minus 1. So this is an example. It's very rare that we can compute explicitly this kind of things. The second maybe result that I want to mention is again Milnor-Wolf. So there are two different papers, and it concerns a group gamma, which is solvable. And so there are two cases. Either gamma is nilpotent, and then the entropy is 0. So the growth is polynomial for any generating set. The growth is polynomial for a nilpotent group, or the group is solvable but not nilpotent. So solvable with exponential growth, not nilpotent. And then the growth is exponential. So this is the frontier between exponential growth and polynomial growth and well, non-exponential growth. I'm cheating a little bit. I could add almost. So I might say during the lecture almost nilpotent. So what does almost mean? Almost means that there is a subgroup of finite index which has the property that is almost. Right, but I try to avoid this. Okay. I want to give one example because this example will show up later of nilpotent of a solvable group which is not nilpotent. So start by taking the following matrix with integer entries, and it is invertible in GL2 of Z, and consider the group gamma sub A, which I write like this. So I don't know the which side I should take. So it means that this is a semi-direct product of Z with Z2, and the law, group law, is described as follows. Maybe I should call, I didn't call it X, K prime, X prime, is equal to K plus K prime, and X plus A, K, X prime. I'm just checking that the prime are the right places. Yeah, okay. So you just, when you move one step in Z, you twist in the Z2 direction by this matrix here. So this group is solvable and with exponential growth. And that was already remarked by Schwarz. And it will show up in a minute in a different context. Okay, so these are the basics. So it's a bit annoying to have these two quantities depending on lots of things. I will succeed before the end of the lecture to erase correctly the board. So the idea is to minimize. So we'll define two invariants. So in case one, we'll call algebraic entropy of the group gamma, finitely generated group. So it's written in French, entropy algebraic, as the infimum over all finite generating set of this number. And in case two, we'll call minimal, so this is written in English, entropy of X as being the infimum over all Riemannian metric J, Well, you see by the definition that if we minimize on all Riemannian metric, we can use dilation, and that will get 0. So we have to normalize somehow. And the normalization is given by the volume to the right power. I didn't say that the entropy behaves like the inverse of a distance. The 1 over r gives the way it behaves. And that becomes far more interesting than before. And even, so it's, because it's quite, these two invariants are quite difficult to compute. All right. So let me again give some results. So for case 2, so with two of my collaborators, Courtois and Gallo, in I think it's 95, we were able to show that minimal entropy of a manifold X is equal to its volume when the manifold carries some hyperbolic metric. So these are closed manifold, of course. Hype is not hype, but hyperbolic. So it could be real, complex, quaternion, and even for the octonions. And I think this is one of the rare cases in which we can really compute it. And for example, for those who are familiar with symmetric spaces, there are other locally symmetric spaces, for example, the higher rank symmetric spaces, and the result is not known. Those who are not familiar, I can describe a space, SL3R, mod out by SO3R. So this is a symmetric space, a complete symmetric space, and there are lattices, uniform lattices, and you can mod out. And if you take this as a X, there is a preferred metric which comes from the situation, the group situation. Nobody knows whether this very special metric minimizes the entropy. It could be something else. It could be not a Riemannian metric. At some point, I thought it was a Finsler metric. I was not able to prove it anyway. So this is one example where we were able to compute and to show that it's positive, which is important. Another example is given by a general result by Gromov. Well, a corollary of a general result by Gromov. And it says that for any closed differential manifold, the minimal entropy is bounded below by, well, some universal constant depending only on the dimension, and some invariant which is called the simplicial volume, or sometimes Gromov norm of the manifold. I will not define it because it will take some time, but essentially you write the fundamental class as a sum of simplices with coefficient, real coefficient, and you take the L1 norm of this coefficient and you minimize. So it's a typical invariant a la Gromov. You write things and you minimize on everything, and it's a miracle that it gives something. So knowing this, if you want to show that this is positive, then it suffices to show that this quantity is positive. And it's not too difficult result, which Gromov attributes to Thurston, and Thurston used to attribute to Gromov, to show that if sectional curvature is strictly negative, then this norm of manifold is positive, and we can even give a value in terms of the upper bound of the curvature and some other invariant. And finally, something which is related to the subject of this lecture is a result by Igor Mineyev. who is in this country. I don't remember where. You might know where he is. I don't remember. And the result is kind of nice, actually. If the fundamental group of X is Gromov hyperbolic, then this simple volume is positive. Well, so there's this new word, this new expression, Gromov hyperbolic. Maybe I take the time to define because I will be using it. So a metric space is Gromov. So to be on the safe side, I will take a metric space which is so-called proper. Maybe it's not necessary. Proper means that the balls, closed balls are compact. Geodesic, this is necessary, meaning that between 2 points there is a minimizing geodesic, a segment which realizes the distance. And I think that's sufficient. And for any tripole of point, I will give this definition in 2 different ways. Since it is geodesic, you can draw a triangle like this. And we say that X is said to be delta hyperbolic in the sense of Gromov if triangles are delta thin. Nice definition. So what do I mean by delta thin? I mean, for example, that for any point on one edge, there is another point in the union of the 2 other edges, which is a distance less than delta 2m. So let me give the name E2, E3.
Are you assuming here that X is a spherical in this result? We perhaps need to
Yeah. Spherical and torsion-free, I think also.
The space X is spherical.
Yes. Sorry. Space S is spherical. So let me finish the definition. So E2 union E3 is less than delta. Okay, so I give this definition, and if the Cayley graph of a group satisfies this, then the group will be said to be Gromov hyperbolic. Okay, so I'll be more precise in a minute. So I can still spend some time giving some other result, and so maybe only two such results. I'm very slow. I'm sorry about that. This is also an issue when you get old. So probably I will need this. So result of Ozin saying that gamma is a finitely generated solvable group which has exponential growth. So not almost nilpotent. Then the algebraic entropy of gamma is positive. And I will need this, probably this result by Malik Kubi, saying that if gamma is a finitely generated hyperbolic group in the sense of Gromov hyperbolic group, then the algebraic entropy of gamma is positive. Well, under the condition that gamma is not elementary, non-elementary. And non-elementary means that it's not finite, and it's not z up to a finite index. So z is not included in gamma up to a finite index. Finite index. Okay. Okay, so the question that I want to discuss now is there any relation between these two invariants where we got rid of the metric on one side, on the generating set on the other side? And the answer to this question, of course, is no, in full generality. So what are relations between I1 of x and mean entropy of x, and so the answer, there is no relation. And I'll give two examples. So the first one is related to, again, to this construction. So we take the same matrix, and so since the coefficients are integer and this matrix is invertible in GL2 of Z, it acts on the standard torus T2, R2 divided by Z2. And so I make this mapping torus construction. You cross it with 0, 1, and you mod out by the relation, which is 1, x is identified to 0, a of x. So it's a twisted, you twist the by a the product in order to have a manifold which fibers on the circle. And so this is a manifold which I will call XA. So XA can be endowed with a natural metric, and the fundamental group is the group gamma A that I introduced before. So it is solvable. So the growth in the universal cover is exponential. However, we can check the following. So there is a sequence of metric which collapse on this space. So collapsing means that the sectional curvature is bounded. And from this, we can check that the entropy is bounded. Constant. Along the collapsing, whereas the volume goes to 0. So in other words, the minimal entropy of this manifold is 0. On the other hand, because of this result, the algebraic entropy of the fundamental group is positive, right? Okay. Of I1 of XA is positive. One of the relation that you can imagine, namely this bounded above by the minimal entropy, is not possible here. And the second example, which is important for the rest, the second example is the following. So take, for example, an n-dimensional hyperbolic manifold, closed. And I cross it by some projective space. So the thing I didn't say is that I want to take an orientable manifold. So let's, for example, cross with the RP3. So it's a manifold of dimension n plus 3. And we can consider a sequence of Riemannian metric on this manifold, which consists just in collapsing the RP3 part. So, which I write this way. Okay? So first, when you live to the universal cover, you have a S3 factor, and the entropy doesn't see it. So in particular, entropy of xn of yn plus 3 epsilon with this metric here is constant in epsilon. So if when you look at the growth of balls, there is a factor which is the sphere, but when you take logarithm and divide by r, this disappears completely. Right? And again, the volume goes to 0. Plus 3. Oh. On the other hand, it's easy to check that the fundamental group here is hyperbolic. Hence again, the algebraic entropy of the fundamental group is positive, whereas mean entropy here is negative, is 0. Okay, so these two examples will be helpful in the sequel. So let me state a result. Yes. So, main results. The main result for this lecture. So, theorem 1. So, so x dimension n, which I assume to be orientable. Essential, I will define this in a minute. Closed manifold. B, I need to have n divided by 2. If pi 1 of x is delta hyperbolic, non-elementary, and torsion-free. So, to define hyperbolicity for a group, I need a generating set. And especially, I want this number to appear. With respect to some generating set S, so certainly the entropy of gamma with respect to S is positive. I will assume that it's bounded above by some number h. So the reason why I could take h equal to this number, but I want to work on a class of groups. So let's put a threshold here. Then the mean entropy of x is bounded below by some constant which depends on the dimension, on delta, and on h, and which is positive and more or less computable. All right, so to finish the statement, I have to explain what essential is. So take x. So this manifold has a classifying space, B pi 1 of x, and you can look at the standard map into the n homology of the classifying space. And essential means that you require this map to be non-trivial, non-zero. I'm sorry. Okay. All right, so it's very strange to have this threshold, but we can now consider a whole class of group. As I said at the beginning, upper bound on the entropy corresponds to a lower bound on the curvature. It turned out that if you take the time to think a little bit to the definition of delta hyperbolic, you'll check that the delta here corresponds to a lower bound on the curvature. And so this is, now I'm explaining the other title. This is somehow a curvature-free estimate where the lower and upper bound of the curvature are replaced, one by an asymptotic invariant and one by this delta coming from the definition. All right. And of course, when you look at the definition of delta hyperbolic, local geometry does not play any role. I mean, it's something on the large scale geometry which is interesting. Yeah, well, so there is a corollary which is a bit trivial, but let me state it. I'm really slow. So a corollary, a stupid corollary is that in this situation, same assumption, then this minimal entropy is bounded below by C and delta H divided by H times the algebraic entropy of the fundamental group. Of course, this is stupid just in putting this inequality above. But just to show that in this situation, the counter-example are avoided. Nevertheless, they show that all hypotheses are necessary, which I guess you would have believed. So for example, this example here, the group is not hyperbolic. On this example with the projective space, then the group is hyperbolic, but there is torsion. So the torsion-free hypothesis is necessary. And the essential hypothesis is also essential. You can see it by, so this space is essential, right? But if you put S3, you get a similar example. The space is not anymore essential, and so essential is essential in this statement. All right. So let me give, not the proof, certainly not, because I'm really extremely slow. So the two remarks that I wanted to say is that these examples show that the hypotheses are necessary. We are not really satisfied with this constant here. The question is now, is it necessary to have this number involved here? To be honest, I don't know. I don't know if the answer should be yes or no or whatever. So it's not really satisfying, but that's what we can do at the moment. So I'll give the structure of the proof, not the details, right? And I'm pretty sure you don't want to see the detail today, at least. So the proof relies on the use of several of two theorems, but before I have to define some quantities which are interesting here. So the first one is the so-called something that we call Markoulis Constant. And the Markoulis Constant for this space here, is defined as follows. So it depends on the metric. And it is, so for the sake of simplicity, the fundamental group will be called gamma. So it's the supremum on these real numbers R, such that gamma R of X is cyclic, is a cyclic group. I will define it in a minute. For all X in X. So gamma R of X is the subgroup of the fundamental group, gamma, generated by loops, or by classes of loops, I should write, of length less than r. So this is classical Markoulis constant. Usually, here we put almost nilpotent, but we are in a negative curvature context. We are in hyperbolic space, so cyclic is sufficient. Right. So this group, this constant describes the thin part of the manifold, which in that case look like cylinders because the group is cyclic. All right, so this is the first inequality. The second point that we need is the so-called field radius. So we start by the Kuratowski isometric embedding. So any metric space can be, well, in any, so here we have a manifold and we consider it as a metric space. And we can embed isometrically into some Banach space, which is exactly L infinity of x with its standard norm. And the embedding is obvious. You send x to the function distance to the point x. Right. Now, when you look at, let me call it iota. You look at iota of x, and you will be looking at the smallest tubular neighborhood in L infinity, so that the image bounds. So let's define the filling, or maybe I'll write it here. Let me define the filling radius of x to be, so which definition should I take? The smallest epsilon positive, such that the image of the fundamental class is equal to 0 in tubular neighborhood of radius epsilon of E of x. So it's a loosey way to write it down, but you understand what it means. We're looking at the image of the manifold into this Banach space and try to fill in a tubular neighborhood. And the smallest tubular neighborhood give rise to a number in which you can fill in, give rise to a number which we call filling radius of x. And this is a theorem by Grenoble, which shows that for any closed differentiable manifold, orientable, so there exists C of n such that for any closed orientable, well, I put orientable because I don't want to bother with the coefficient in here, orientable differentiable manifold, x, then the volume of x for any metric is bounded. So let me check the constant. Yeah, it's bounded by C of n filling radius of x. So it's related to some metric g to the n. Right. So a priori, we don't know if this is positive or not. But then one key ingredient in our work is a result of the next speaker, Stéphane Saboureau, which is the following. So a result that we interpret, the result is much more interesting than that. Take x dimension n. essential closed manifold, maybe n greater or equal to 2. And we assume that the fundamental group is non-elementary, hyperbolic in Gromov's sense. Say delta hyperbolic. Well, delta doesn't matter here. Torsion free. And if we assume that there is a finite generating set so that the entropy of the fundamental group oh no, I'm sorry, I realized that I was about to say something stupid. Yeah, so was non-elementary, then it's much simpler, so don't need finite generating set. Then the Markoulis constant of the metric, so we start with the metric, Riemannian metric, is less than 8 times the filling radius of xg. And in particular, the volume of the manifold is bounded below by some universal constant depending on n only times the Markoulis constant to the n. So that's one of the ingredients. I'll give the second one, and unfortunately I won't have time to describe anything seriously. So probably stop there. So there is a second. So this is a nice result. It gives some explicit bound from below on this very weak invariant here. And the second ingredient is a theorem of ours, which is some kind of a Tits alternative. So we start with a group gamma and a finite generating set. The group is non-elementary, torsion-free, hyperbolic, I should say delta hyperbolic because I need this delta for this generating set. Yeah. And we assume that the entropy, well, it's not really an assumption, we call H an upper bound of this quantity. Then for any finite set, sigma included in gamma, if we call G the group generated by the element of sigma, so the group is a subgroup of gamma, then the alternative is the following. Either G is cyclic or the algebraic entropy of G is bounded below by some universal number and H. Right. Okay, so I'm close to the end. I don't think I can go further. I will write one more theorem and try to do quickly something. It would be stupid. It's better to stop here, well, before and to stare at these two results. So this one is some kind of Tits alternative. So for those who are not familiar with group, Tits alternative says that for a linear group, so a subgroup of GLN of R, for example, it has either polynomial growth or it contains a free group. But when one has a free group, when in a group you have a free group, then it forces the growth, because the free group grows very quickly, exponentially. And so this is a version for this situation, where instead of free group, we compute the algebraic entropy and give a lower bound in terms of these two invariants, which are really curvature-like but more asymptotic in some sense. And how to get an estimate from below? Oh, I should put this. How do we get an estimate from below of the algebraic entropy? So which is the growth of the group of the Cayley graph for any generating set, finite generating set. Well, the way to get this is to produce free group or to produce free semi-group, which is much easier. So free semi-group is a group which is free only for when you look at words with positive powers. So there is no relation, none of the words with only positive powers in the generators, none of the words in the generators with positive powers are equal to the identity. It could happen if you put some negative power, but not with positive. So the way to prove this, which is actually a bit technical, is to produce free semi-group in this situation. And OK, so once we have these two theorems, it's quite easy to get the main one, which I probably erased. Never mind. And I think it's better to stop here. Thank you very much.